So that's the last week of this course, week 7, just before the exam. Well, if you think that this is too soon or that we should, let's say, postpone this deadline, that's possible. So maybe we can already discuss now. Is this okay for you, or is this too early? Should we just postpone this deadline? Because personally, I'm also fine with having a deadline at the end of the exam week, because there are no presentations. I mean, I can just correct at the exam of the end of the exam week. You'll have more time. But it also means that if you do not, let's say, schedule or prepare well, you have to work on the case during your studies well in the exam period. You can still hand in earlier if you want. So what do you want? Do you want this deadline, or shall we set a later date? Do we need to vote?
For me, this is fine.
This is fine. Are there others who want to have this postponed? Okay, because then I think we decide to keep it like this. And if somebody wants to have a later deadline, then contact me by email. But do not do that on this Friday, but do that this week. Okay, then we can discuss this week what the deadline will be, and then we stick to the deadline that we discussed. Okay, then I also have an overview of the remaining lectures. So the lectures will continue as we discussed. So today I'll be talking about the answers to the exercise that you made. Tomorrow is a guest lecture. I'll come back to that in a minute. And I'll also give 2 lectures on mixed integer recourse models. And this was the topic of research that Marcus van Berg and I did for the last 4 or 5 years. So I want to say something about that. It's generally also part of this course. You can see it in the lecture notes. So it's chapter 4, sections 1 till 3. They're about integer recourse. The last 2 lectures are given by Professor Teuter, and he will give some lectures about how stochasticity, so uncertainty, appears in his research, so in several OR applications. And I don't know exactly what the content will be, but he will inform you in time about that. So if we compare this with the, let's say, schedule of the course as it was, I think there are 2 major changes. So we do not have the presentations anymore. That's one change. And the other change is that we're not discussing section 3.4 anymore. So that was on algorithms for recourse models. I probably will say something about that when I discuss these mixed integer recourse models, but you are really welcome to study this material yourself. If you have questions, you can ask me, but we're not going to discuss it during a lecture, and it will also not be part of the exam. And so this is, let's say, the setup of this course. Are there questions about this? Is anything unclear? Yeah, okay.
The weight is put on your grades for your assignment and case study, are they still the same?
Yeah, so the grade is determined in the same way. Usually the presentation was also part of the grade of the case study, but now we just don't count the presentation, so just the grade for the report for the case study. That will be the grade for the case study, and the rest is the same. And the exam is still part open book, part closed book. I don't know if you already discussed this together, but the idea is that in the beginning of the exam, for the first question, you can use the book, so it's open book. And, when you're finished with these questions, you hand in that part, and then you can, let's say, you have to put away your book, and you can work on the other exercises. Okay. Other questions? Now, if there are any questions about the setup or on the case studies, for example, you can always email me or ask me during the break. Okay? Then tomorrow there is a guest lecture from Peter Pekas. He's from the University of Corvinus University of Budapest. And And Peter was doing research with Maarten Verk, and actually he studied here for his master already many years ago, and they kept doing research together. And he was planning to visit. He always visits once a year, and they plan to visit last week and this week. So he is here. Usually he gives a guest lecture, so we will talk about the research they do or did together. And I think it's an interesting topic because they are considering, let's say, for railway scheduling, so with trains, how much supplements to add on each part of the trip. So for each part of the trip you can add some extra time to, let's say, compensate for possible delays. And well, in which way, how do you divide this extra time over the entire trip? To make sure that, well, there's as less disturbance as possible. This is kind of the idea of the guest lecture. So he will be here tomorrow. I won't be here because I have to teach another tutorial, but he will give this guest lecture. I think it will be very interesting. And also I put the abstract, I will put it on Nestor so that you can read it before tomorrow. Okay, then I want to move to the exercises that you made. So these are the handwritten notes that Maarten used, and I want to use them for here today. So I know it's not in terms of presentation maybe not the easiest to read, but is it possible to read in the back? Because otherwise I will zoom in.
The little one.
Sorry?
You make it a little one.
Yeah. So then we are going to look at it in a different way. We're going to do something like this. Is this better? Yeah. Okay. Then we're going to do this. So I've corrected and graded the exercises, and I think in general you really did well on these exercises. So I have put some feedback there as well, so you can take a look. If you have questions about the feedback, you can ask me. And of course you only made one of these exercises, so I want to discuss, let's say, the solutions here today. For obvious reasons, this will not be on Nestor. So if you want to make notes or something like that, you can do that. Okay, I think we're just going to see how far we get with this exercise. If we finish early, that's fine, and otherwise we continue on Thursday. And I want to start with the second exercise, this R2, which is about recourse models, and in particular on recourse on, let's say, complete recourse and sufficiently expensive recourse. I don't know if you already discussed these terms, what it is, probably you did, because I think that's what we usually do. And we have this recourse model, and I'll also write down, let's say, the second stage value function on the blackboard, because it's useful. We have a recourse model in canonical form. And so in canonical form means that the variables are all non-negativities, the equalities, the inequalities are all equality signs. So we want to minimize our first case decision x, which are greater than equal than 0. We have some direct here and now cost c times x, and we have some expected recourse cost q of x, and we have to select our first case decision x such that ax is equal to b. And qx is the expected recourse cost for satisfying these random goal constraints h omega minus t omega x. So you can see here that the h, which is usually the right hand side, and the t of omega, those are the technology constraints. Those are random, so they depend on this omega, and x are the decisions. And the second stage value function, it somehow tells us which recourse actions y we can take. And the second stage cost are q, and so the cost are q times y, but they have to satisfy this equality wy equal to z. And so here we are interested in this second stage value function, is b of c, which is the minimum and we're going to look at this particular problem, and we want to know when this, let's say, recourse model is complete and when it is sufficiently extensive. And so we know that this recourse model is complete if this value function, so phi of c, is finite, or d smaller than plus infinity, for all possible z. And what does it mean? It means that there always is some feasible recourse action. And because if there is no feasible recourse action, then the feasible region of this minimization problem is empty, and then we say that this minimum equals plus infinity. So there should always be a, let's say, feasible recourse action. But somehow, this is equivalent to, or at least that's what we have to show, to the fact that this set, these lambdas, that this is a bounded set. And, well, you might wonder where is this set coming from, but if we look at the dual of this value function, it's a maximization problem of lambda times c, such that lambda w is smaller or equal than q. And this lambda is a free variable, so there is no non-negativity condition. Why? Because we have an equality here. So because here is the equality, lambda is free. So this is really the dual of this value function. And now you can see that this part here, these constraints, this capital lambda, is just the feasible region of this dual problem. So that somehow the matrix W is complete recourse matrix if this dual region, feasible region, is bounded. And then somehow this is the same as this expression, that lambda times W smaller equals 0 implies lambda is 0. And who can explain why these two are the same? So this is about something bounded, and here we have some kind of implication. Okay, now suppose what happens if there would be some lambda different from 0, for which lambda W is smaller or equal than 0. What would happen then? Well, if you have some feasible lambda here, and you can add a lambda for which different from 0, for which this is smaller or equal than 0, well, you can increase it, and you can multiply it by some scalar, and this always will be smaller or equal than 0. You can add that to your lambda here, but because it's smaller or equal than 0, then the one you found will still be feasible. So you can add a very large factor to this problem, and so this feasible region will not be bounded anymore. So basically, if you find a lambda which is not equal to 0 here, then you found a direction in which you can always move indefinitely in your feasible region, which are still feasible. And so if that's not possible, well, then you know, okay, this will be bounded. That's the idea. So let's scroll a little bit to see what we have here. Okay. So maybe what's important to mention is that in this LP duality, usually you have strong LP duality, the primal and dual, they are the same. These two, usually they are equal. And of course there might be some problems if one of the two is plus infinity or minus infinity. And so that's what we have here. We have LP duality, this primal problem phi. It's a minimization problem. It's always greater or equal than the dual, which is a maximization problem. And normally they are just equal. and there is just one exception. It might happen that both the primal and the dual are infeasible. And in that case, the primal is plus infinity and the dual is minus infinity. So that's what we have to take into account, that this primal and dual are almost always equal unless this case arises. Okay, so let's look at the problem. So we're going to prove this statement here. And we're going to do it as follows. So suppose that W is a complete recourse matrix. If that's true, then we know there always is a feasible recourse action. So the second stage value function is always finite. And for all Z, and that's important, for all Z, it's finite. And then we know, since the primal is not infeasible, we have this strong duality. They might be both equal to minus infinity, but let's consider for the moment that they're just finite, they're equal. If we then look at this dual problem, here, or then the value function is equal to the dual that I wrote down here. It's the same. This dual problem, and it's finite. But it's finite for all values of C. And you have to imagine, suppose that there is this feasible region here. It's not bounded. So if the feasible region is not bounded, then we for sure will be able to find some cost factor C. C here is the cost factor. If a particular cost factor, we will make sure that this goes to plus infinity. So we cannot have, let's say, an unbounded feasible region, because that will give a contradiction with this plus infinity. And so we know, because this is true for all Z, that the dual feasible set is bounded, and that's exactly what we had said before, and then this must be true. Otherwise there's a direction of recession, and so there you can increase, so we know this must be bounded. Okay, now we're going to do the same with the other way around. So we're going to assume that this dual feasible region is bounded, and we want to show that the recourse is complete. And here we also have to take into account that it is non-empty, because if the feasible region is empty, we might again have this case where primal and dual are infeasible, and then we might have problems. But if that's okay, then we know that the dual is smaller than plus infinity. So why do we know that? Why is this dual smaller than plus infinity? Yeah, because the dual feasible region is bounded. For example, we know there are finitely many extreme points of this dual feasible region, and well, the maximum will be one of the vertices. It's a bounded feasible region, and at least we know for sure it will be smaller than plus infinity. So because it's bounded and non-empty, bounded it's smaller than plus infinity. If that's true, then we have strong duality, and then we also know that, let's say, the original function is smaller than plus infinity. And if that's true, well, that's basically the definition of a complete recourse matrix, but then we know that a feasible solution must exist. So that's very interesting. So complete recourse is related to boundedness of the dual feasible region. If the dual feasible region is bounded, then the recourse is complete. Okay, so the second part, we need to show that this Q is sufficiently expensive. And again, somehow this is related to the dual of this value function. So we can give or characterize these recourse models, so when they are sufficiently expensive, by looking at the dual. And we have to show that this Q is sufficiently expensive if there exists some lambda for which lambda w is small or equal to q. And you can see again here, this is related to this dual feasible region, lambda w is small or equal to q. And basically it says there should be a feasible dual solution, so the dual feasible region should be non-empty. And that's what we need to prove. And okay, let's start with the assumption that q is sufficiently expensive. Well, then we know that phi of z, the second stage value, is larger than minus infinity for all z. And okay, now we're going to select a particular z equal to 0, for which we know that the value function is not plus infinity. And this is, let's say, a small subtlety that some of you missed in the assignment, because some of you said, well, we need to assume that the recourse is complete. But that's not necessary. So I don't know whether the recourse is complete, but I'm going to select a particular value of the c bar, for which I know that phi of c bar is smaller than plus infinity. And it says here that we should take, for example, c bar equal to 0. And I'm also looking here at this original value function. And who can explain why for this c bar is 0, the value function is smaller than plus infinity? So why is this finite? So here's the value function. So why is the value function finite when c bar is equal to 0?
Take y is 0.
Yeah. And so if c is 0, then a feasible solution is equal to 0. And if we have a feasible solution to this minimization problem will never be plus infinity. So for this particular value of c bar, we know that the value function is smaller than plus infinity, but then we can apply strong duality. Then the primal is equal to the dual, and the dual was given by this. So the primal is equal to the dual, but the dual is larger than minus infinity, because that's what we started with. We assumed that q is sufficiently expensive, so you can see it here. So it means that this maximization problem is larger than minus infinity, but that means that the dual feasible region cannot be empty, because the only way that this maximization problem is minus infinity is if the feasible region is empty. And that means there should exist a feasible solution. And so lambda is feasible. Okay, now the other way around. So I think this is the easy part. So if we assume that the feasible solution exists for the dual, we know that the dual is larger than minus infinity, and by weak duality the primal is always larger than the dual. So the primal should also be larger than minus infinity for all z. And so what's interesting here, and that's also something we often use in stochastic programming, is that this dual problem, it doesn't depend on c. So the dual feasible region doesn't depend on c. And so c is just the cost of the dual, and well, basically that's why we immediately, if we look at this dual, we get information for all c, for all cost parameters. Okay, now the final remark is that the special case is when q is greater or equal than 0. So here you can see this primal problem. If q is greater or equal than 0 and y is greater or equal than 0, well, it makes sense, right? We can immediately see that this problem will be sufficiently expensive. Whatever y we choose, q times y will always be greater or equal than 0, and thus larger than minus infinity. But you can also derive that using the dual information. Because if q is greater or equal than 0, then look at the dual problem, then we can always select lambda is equal to 0, and that will be a feasible solution to the dual. So that's what's stated here. 0 is an element of the dual feasible region, and well, that's what we said, what we needed, that there should the dual feasible region should be non-empty. So that means that for Q greater or equal than 0, we know immediately it's sufficiently expensive. Are there questions so far on these two things? No? Because now the idea is that we're going to apply what we've learned to two special cases. And one of these special cases is our favorite special case, it's the simple recourse case. I think you've seen that a lot already, simple recourse. So this W matrix is equal to the identity and minus identity. And the Q for Q, we just use Q plus and Q minus. And these plus and minus here, they're just indices. So those are not the positive or negative part of Q. They're just indices to denote that the Q plus corresponds to variables that are usually the positive part of the right-hand side, and the minus corresponding to the variables that will give us a negative part. But the most important, they're just indices. And the question is, for this simple recourse problem, when is it complete? Okay, then we think about complete. Well, complete was related to the dual feasible region, but that was bounded. And so bounded, it basically said that if we remember that lambda W smaller than 0 implies lambda equal to 0. This was for complete recourse. And here, this first part, you can see lambda times W smaller equal than 0. And the question is, okay, does that mean that lambda is equal to 0? Well, this is smaller equal than 0. And basically, you get two types of equations. You have lambda times I, the identity, which is just lambda. Lambda is smaller equal than 0. And also, lambda times minus I, so minus lambda smaller equal than 0. Well, that can only be true if lambda is 0. So we immediately know that lambda W smaller equal than 0 implies lambda equals 0. That's true. Okay, then sufficiently expensive, and that was their exists lambda such that lambda W is smaller equal to Q. So the dual feasible region is non-empty. And so this is sometimes more difficult for students, because now we're looking for, let's say, values of Q for which the dual feasible region is non-empty. And so, this is the equation, lambda W smaller equal than Q. And you can see that that's equivalent to lambda smaller equal to Q plus and minus lambda smaller equal to Q minus. And now the question is, well, of course, you also want to solve this. It's not really solving it for lambda. You want to find for which values of Q plus and Q minus there still is a solution. So that's a different question. And you can see, well, if this has a solution, well, then we really need this minus Q minus smaller than Q plus. Because these two equations are equivalent to this. And so there only is a feasible solution if Q plus is larger, or at least as large as minus Q minus, and that's the same as Q plus plus Q minus is greater or equal than 0. And maybe you already saw this when you discussed the simple recourse models, and that this is what you need for sufficiently expensive, and you can also derive it using this result. So using these expressions. Okay, now the second example. There we have the second stage value function, and it now somehow involves the maximum. And so in simple recourse, basically we're penalizing any deviation from one of the goal constraints. And under this structure, where I have this maximum, we're only penalizing the maximum deviation of the goal constraint. So it's a different type of model, but it's still a recourse model because, well, we can introduce the variable y And we add the constraints y greater or equal than ci. And because if you solve this minimization problem, and then you'll see that, well, y has to be larger than any ci, so it has to be larger than the maximum of these ci's, and y should also be positive, or greater or equal than 0. So really, this is equal to q0 times the maximum of the ci's positive part. And of course, here we have these inequalities, but we can transform that into the canonical forms with equalities by adding slack variables. And then we have the y minus some slack variable. So then the W matrix, and that corresponds to these slack variables, will also look something like this. And here I have 0, here I have 0. And so every row corresponds to one of the constraints. So y minus a slack variable is equal to zi. And you can see that the first column, which is this E over here, it's a column with only ones, and we have minus the identity here. And so that's the same structure, and for this particular problem we can write Q equal to Q0, and well, the slack variables do not have any cost. So the cost parameters corresponding to the slack variables are 0. Okay. Now, let's try to find out when this model, or if this model is complete, and when, for which values of Q, it's sufficiently expensive. And so for complete recourse, we want to know whether the dual feasible region is bounded. And we want to know if lambda W smaller or equal than 0 implies lambda equal to 0. Well, lambda times W. If I multiply the first two parts, I have this lambda, which is a row vector. I multiply it by this column vector, column with only ones. So lambda times E, I basically have to sum up all the components of lambda, so that really is the sum of these lambda i's, and it should be smaller or equal than 0. If I have lambda times the identity, I multiply this row vector times a matrix, and I get many constraints. For each I get a constraint. I get minus lambda smaller or equal than 0, which means that every component is smaller or equal than 0. But this one here, minus lambda I smaller or equal than 0, is the same as lambda greater or equal than 0. So if we want to find a lambda satisfying these two equations, well, it has to be greater or equal than 0, the vector. But if I sum all the components, that should be, well, negative or at least not positive. So there really is only one way in which I can solve this system of equations, and that's when I select every component of lambda equal to 0. And that's what we want. We want to show that if lambda W is smaller or equal than 0, the only solution to this system of equations is lambda equal to 0. So this really means we have complete recourse. Okay, that's sufficiently expensive. So remember, we want to know for which values of Q this dual feasible region is non-empty. So for which values of Q does there exist lambda satisfying this equation? Well, again, we have the sum of these lambdas is smaller or equal than Q0, but every component is, the minus of the component is smaller or equal than 0, the component itself is larger or equal than 0, and that's because the Q here is Q0 and the zeros for the slack variables. So these zeros here correspond to these zeros over there. And again, this can only be solved if I take a lambda for which the sum of these lambdas is between 0 and Q0. So if that's the case, then I can solve it. But if Q0 is negative, then I have a problem. So if Q0 becomes negative, I want to select a lambda which is all positive, but if I sum all the components, it should be smaller than a negative number. That's not possible. And so only if Q0 is greater or equal than 0, I can find a feasible solution. And so suppose Q0 is greater or equal than 0. Who can give me a feasible solution for this system?
0.
Yeah, 0. 0 is a feasible solution. And of course you can find different feasible solutions that depend on Q0. And maybe you want to take Q0 divided by the number of variables divided by n. That will also be feasible. But lambda 0 is always a solution if Q0 is greater or equal than 0. And if Q0 is smaller than 0, there are no solutions. So we know that this problem is sufficiently expensive if Q0 is greater or equal than 0. Okay, so this is the first part of the exercise, or this was one of the exercises, and it's the first part of exercise 2. And let's continue with part D. So now we have the same model, this recourse model, and we had some random parameters in this model. So now T omega and H omega, we're going to replace them by their mean values. And so, of course, they're random, but let's replace them by the mean, and that's what we call the expected value model. Okay, so the expected value model, and we have to, we can write it in at once with both the first stage variables and the second stage variables. It's a little bit strange to have these second stage variables because there's no uncertainty anymore, because these T and H are not uncertain, they're just equal to the mean. And, okay, this is what we need to solve. And you might wonder, it's also a bit strange, right? Because usually we have this recourse structure, because we take our first stage actions, while we do not know some of the data, so some information is unknown. And then when something bad happens, we can use our recourse actions Y to compensate for that. But in this model, we already know the let's say, uncertain variables. Everything is known when we make our first stage decisions. So it will be really strange if we select first stage variables or Y positive. Well, it would mean that we already are going to use these recourse actions in advance. While we could also make sure, using the X variables, that we do not need them. And so if these recourse actions are really expensive, that would mean that we do not need these Y variables. And so under which conditions is this true? That we do not need the Y variables, and if we do not need the Y variables, basically we need to solve just this problem only in terms of the first stage variables X, where we do not have the Y variables, so we have the direct cost C times X under the first stage constraints, and these random goal constraints should be satisfied. And the first part, and that's the only part I want to do before the break, is to show that, well, this expected value problem, it's a minimization problem, and it's smaller equal than that of the LP problem. And the first step is really easy. So if LP is plus infinity, then, well, it doesn't matter what EV is, this inequality is always true. Right? So it doesn't matter what EV is. If LP is plus infinity, this inequality is always true. If LP is minus infinity, well, it means that somehow this problem is unbounded, and because we're minimizing, and if I want to have minus infinity, this problem should be unbounded. But then basically, that problem will be unbounded too. You can always use Y is 0 and use the same X variable. So then this is also unbounded. Okay. And now suppose that this is not the case, so there is some optimal solution which we call X bar, and it has some optimal values, C times X. And what's important is that if we select this X bar again, and Y is 0, this is still a feasible solution for the expected value problem with the same optimal objective value. Let's take a look. If I have a solution to this LP problem over here, or maybe one solution, if I use that solution in the expected value problem and use y is 0, so if y is 0, then the qy and the wy, they disappear. And, well, the solution there is also feasible. Of course, the solution, if the solution is optimal here, it's not necessarily optimal there. So here there might even be a better solution. And that only means, and that's the reason why we have an inequality and not an equality. And because, and that's stated here, this solution x bar 0 is not necessarily optimal for the expected value problem. So the expected value problem is a minimization problem. It might be even smaller. And we really can have this strict inequality. And in that case, we're using these recourse actions somehow in this deterministic problem. So somehow they're probably cheap. And we're saying, well, yeah, I want to satisfy this goal constraint. But, well, I know I have very cheap recourse actions in the second stage. So let's do that not now in the first stage, they're expensive. And let's do that in the second stage. Well, and that's not really why we have these recourse actions. And that's why we're interested in conditions on these recourse actions such that we're sure that in this expected value problem, we're not going to use y. And that's what we're going to do